you very much for inviting me here in, well, it's morning here in Boston, but virtual lunch, so to speak. As was mentioned, I gave a presentation on Verilator about, I guess it was 3 years ago now, so time kind of flies. So for this presentation, I'm going to go through some of the introduction of Verilator for those of you that haven't heard about it before. But I'm going to focus mainly on a lot of the changes that have occurred in Verilator over time, some of the learning, some of the things that there's still a bit of work left to do, and some of the successes. So we'll begin with, what's the point of this? Why would you even be interested in Verilator or open source simulation? I'll get it then into what have been some of the changes, kind of bring it into the modern era. What was successful, what not so successful. If you want to run it, how do you run it? How do you use it? What happens if, God forbid, you find a bug? And then, of course, conclusions and questions at the end. Obviously, since it's a webinar, we'll save the questions for the end to make it easier. So moving into why you might want to use Verilator. So Verilator was obviously designed to solve a problem. Originally, Verilator was designed for CPU and system design. And this had a little bit different requirement from what was traditional for simulators of the day. We actually wanted to take a Verilog model rather, and combine it with the C++ and later on System C model. And in this paradigm, basically, you want C++ to own the main loop. You don't have a simulator per se owning the main loop because you have all this C code emulating the processor and all this other code. And what you really want to do is you really want to be able to translate Verilog code into C++ because then you have a full C++ environment. And that has a lot of advantages. You can use all the very good C++ design tools. You can run debuggers. You can run valgrind. And it also provides some unique advantages if you want to combine it with other languages. For example, there's a tool out there that takes Verilator code and pulls it into MATLAB. And that gives far faster simulations than what you would get if you tried to use a simulated bridge to MATLAB, because the code is basically native C++. MATLAB doesn't even need to know it came from Verilog or anything like that. So that's the point of Verilator. And to do this, it's really a synthesis tool. It's closer to a synthesizing tool than it is to a simulator per se, in that it follows the synthesis rule subset. And you get a design much closer to what you get with synthesis than you do with a simulator. So this means things like time delays are ignored. And it's only a 3-state simulator, so it understands tri-states for combining buses. But it doesn't have unknowns. So rather than dealing with X's as a simulator does, it actually randomizes them. There's a few other possibilities. And in terms of finding reset bugs, this is actually a better methodology than X's. There's been a number of papers on that topic separate from Verilator that if you're interested, you can read up why X propagation is not really the best way to find reset bugs. Okay, so the performance of Verilator is generally pretty good. Obviously, mileage can vary terribly, or a lot, I should say. Here's a few things of benchmarks people had run against Verilator. So booting Linux, there was a great amount of success on the MIP score in this case. It was quite a bit faster. Running something like a test builder, which is a C++ sort of environment that was popular a few years ago. Performance was found to be very similar. And basically this was because almost all the runtime was being spent in the test bench. And then there's an embedded CPU example that's actually on the Verilator website based on an open cores model that can run on a whole ton of simulators. And here you actually see a pretty good speed up too. So this was taken right off the open cores website, so you can run that if you want. There wasn't any sort of tuning done for that. There's quite a few users, some of whom we're fortunate to have talking to us later today. Some of the biggest companies are using it. And, if you kind of look for a theme here, one of the common themes is CPU design, and obviously chip design also. But, it's interesting that since Verilator was designed for CPU design originally, that still seems to be kind of the largest following. Why might you want to consider open source? Well, obviously, people always like the cost of open source. This is, of course, if it does close to what you need. It's obviously much more cost effective. Having an open license is also very valuable and actually required for certain applications. For example, NXP has some processor chips, and they wanted their developers to be able to use that, the model of their chips, and they couldn't contact a license server because it's just developer laptops. So it's very valuable not to have a license. And it also lets you negotiate from a much better bargaining position when it's time to actually buy real commercial licenses. They know that you're using Verilator, and they know that there's an alternative to their simulator, and suddenly, magically, their prices get decreased. So big surprise. And having source code, of course, is a good thing. If you want to reuse it to do something different, or you want to try a new language feature, and you can try it out and see if it works. And that's actually a very strong indicator to the language committee that if you say, well, I tried this, I modeled it. If I do it, the code is, the following less dense, and it works very well. etc. And of course, if you have bugs, you can very quickly fix it by having source code.
Hello, Wilson. My apologies. The sound is fading in and out.
Okay. Let's see. We'll try this.
Thank you.
The danger of headsets. I wish I could afford a plane flight there. Maybe next time we'll take a work vacation and be in person. So on the downside of open source, obviously the first thing is support. You or whoever it is in your organization that deals with Verilator is the first level support person. So there's no guarantees that someone else is going to fix your problem, as with most open source tools. But the key thing is you could fix it. So a lot of the bugs are not really that hard to get into. Some are, but most of them are relatively straightforward. So if you want to, you can get in and you can make a quick change. And there's been a lot of people that have done something like that and fix the problem in a few minutes that otherwise you'd have to feed through some bug committee at the EDA tool and wait for the next release, et cetera, et cetera. And one of the other advantages of open source is if you make a change, you actually feed it upstream and it's accepted. Others tend to maintain it, so it's not something you need to deal with basically for the rest of your life. The community kind of deals with keeping it up. Another alternative that's just starting to gain traction, at least with Verilator, is you can actually hire some consultancies that are willing to offer paid support. So this makes it look a little bit more like a commercial tool in the sense of support, but it still has all the advantages of open source. And they then tend to contribute the changes upstream, and it gets supported by the community. And just we talk later about this. So what have been some of the changes along Verilator since it got started? Well, the first thing is, I certainly, even though obviously I've done some verification in my life, I'm getting much more respect for self-testing. Self-tests are very important. Originally, Verilator was just tested on real designs, but now there's over 500 focus tests. And, being able to change the code and know that there's some sort of life there and that it's not horribly broken is obviously a very good thing. It's become much easier to install some of the requirements that were required to build it or install it and simplified. It now runs on many platforms, and other people send in patches to make sure it continues to run on many other platforms. And Verilator may now, somewhat surprisingly, actually may be people's only simulator. So it used to be that people always had a commercial simulator, and now that's becoming less so the case. So it's been adding lint features and better messages, and that'll obviously continue as more people use it. Verilator now obviously supports SystemVerilog. We'll get on slide in this in a minute. This is probably just a little bit of my whining, but it's really kind of scary how bloated of the language SystemVerilog is. Just in terms of the parser complexity, just in terms of the rule set, is about 6 times as complicated, but some of the features in there are just really, really nasty. It's really kind of an agglomeration of all these crazy ideas, some of which don't really make a lot of sense from a language design perspective. But anyways, Verilog-perl, which I'll talk about more in a minute, which shares the parser with Verilator, supports about 95% of SystemVerilog. And there's still that 5% rough edges, but it's certainly a much more complicated language than was originally anticipated for Verilator. Towards that, Verilator, of course, now supports some complex types. I'll talk more about that in a minute. But the big thing is it's moving forward and supporting with the language. Verilator, even though it started with design only, synthesis only constructs, it's continuing to add verification constructs as time goes on. Some of this was just originally for testing, and now it's used a little bit more as a regular simulator. Things like dotted references, and then the DPI and VPI support in 2010. That's of course still ongoing. Model Saver Restore, which was just added recently. And I suspect if things continue to go well, that at some point it will probably be a full-featured SystemVerilog simulator, which will obviously be a great thing for everyone. Towards that, Verilator has a little bit of event-based in it. It supports things like clock gating, but it's not yet a full hybrid simulator, but we'll probably get there eventually. And one of the interesting things that's in development is actually Verilator, not for Verilog, so what do we call it? VHDL 8 or not? I don't think so, but this actually we work towards getting VHDL as a language and support. Specifically on SystemVerilog, the preprocessor is actually the one area in which it's 100% compliant. It's actually better than several of the commercial, actually pretty much all the commercial simulators. There's a paper on my website where I compared it to some of the commercial simulators, and actually I think it's the most compliant preprocessor there is. It supports some of the SystemVerilog types, the obvious ones, byte and things like that. Package and imports were originally added in 2010, although there's been some extensions and bug fixes recently. Type defs, structures, which was also added last year. Things like operator short-circuiting, and there's still, no doubt a great deal of work to do here. But, basically as the more common design constructs get added to the language, it becomes a lot more attractive to people with SystemVerilog environments. So if this sounds at all interesting, what can you do if you want to run it? So, the real instructions are obviously on the website, but I figured it's worth a slide just to kind of talk about the high-level options. So, the first option, which is certainly the easiest, is if you're running Ubuntu or Debian or some of the common distributions. There's a standard RPM that comes along with your OS, and you can just install it like you would any other RPM. That may not be the most recent version, but it's the one that particular OS shipped. So if you want to just try it, that's a good way to do it. You also can install it and globally download it, make install. That'll install it globally in your machine. The way I tend to run it, and I think most organizations that have large CAD environments tend to run it, is you can make it and just leave it in place in some directory, and then you can point the Verilator root directory at it. The advantage of that is it lets you run multiple versions of the tool. Different people can be running different versions. You can then have it part of your release process to make sure that as you have files in your source code repository that point to a particular tool version, and the tool version will change underneath people as new versions get released. After you've installed it, there's a reasonably small example in the Verilator man page, which you can get by just running Verilator help. And this says here's how to create a real simple sort of hello world file and create a little wrapper and Verilator compile and run it. It shouldn't take you more than 5 minutes. And you can actually now use it as a lint tool. So if you have your own design, you can just say Verilator lint and give it an input.vc if you need one, listing all the directories, and just give you a top-level file, and it'll go off and tell you what it's not so happy about. What does it do after it runs, assuming you're doing more than just linting? Well, basically, the top level of your Verilog file, so here we have this little convert module with an input and output and clock. So this becomes, in the output, a C++ class. So you see a class here, and then there's member variables for each of the inputs and outputs, and then this function called eval. So basically the idea is what your code would do is you would have a main loop, and this creates an object of the converted model here, and you basically keep looping on this eval. So I set some inputs, I then call eval, I then get the output and let time advance and circle it back around. So this is obviously different than your normal simulator. A normal simulator you would have an initial begin, create clocks, things like that. And again, Verilator is more of a translator. It doesn't so much have a concept of advancing time itself. It expects someone else to do that. So it's kind of assuming an embedded model. But in most cases, people that may have, say, a top-level test bench with no inputs and outputs, so this main file gets very simple. And there's actually a bug file that someone would like to simplify the way this works and makes it more traditional. We'll probably do something there this year. What's going on in the inside is there's this eval function, and the way it works is the first time you call eval, it runs all your initial statements and then settles out the logic sort of DC stability kind of checks. And then every other time you call it, it basically looks to see if any clocks have changed, and if the clocks have advanced, and it runs your sequential logic. Otherwise, it looks at the combinatorial logic and advances the combinatorial signals. And then, of course, if you've done a generated clocks or something, it has to go back through this loop again. So one of the ways to improve performance, you can turn on warnings, and it'll tell you if you circle through this loop several times and get some pretty good speed ups by reducing the number of times through the loop. So this is not entirely different from a normal event-driven simulator, but the big thing that is what it can do, it can actually statically schedule the code from top to bottom. So that's one of the ways that if you can minimize the number of times through this loop by optimizing things like generated clocks, you can get some very good speed ups. If, unfortunately, you get a bug, which I know it happens, I'm sorry. The first thing to do is look at the warnings. Verilator, like all other tools, we do test the warning cases, although it obviously gets less testing when people have turned off a warning or ignored something it's complaining about than cases where you have clean code, or what Verilator considers clean code anyways. And the same thing is also true in terms of performance. On the forum, someone actually just mentioned that they got a 2.5 times speed up of their code by turning on fixing a specific warning. The thing probably easiest easiest for you guys, I should say, thing to do is if you have a test case, follow the instructions in the man kit page. So there's an example.v file you can edit to kind of put your own little code in there. And test cases are often actually more important than the code itself. The code for Verilator itself has gone through at least 3 major, pretty much top to bottom rewrites. But the test cases pretty much have stayed the same. So it's very valuable when you change something to be able to run a test and know that it has, you haven't broken anything. So that the test persists even though the rest of the program changes. The other advantage to using this example.v and editing it is it's extremely easy to run it on other simulators. So the test harness in Verilator actually understands how to run on other simulators. So after you've made the example.pl, you can say run on VCS or Icarus or NC or any of there's like 6 or 7 different flavors there. So actually, when I find a bug in any of the commercial simulators, I put it into Verilator format and I can quickly run it across 3 or 4 simulators, and then I can say to the vendor, this works on everybody except for you. What's going on here? So even if it's not Verilator bug, it's still useful. And of course, submit the bug to the website if you can. And if you'd like, it'd be very helpful if you, ask for advice and maybe you can get in there and try to fix it yourself. If you do run with debug, what you'll see is kind of the fundamental important object inside Verilator is an AST tree. So if you read compiler design books, they'll go into excruciating detail on this kind of thing. But to go over very quickly, if you have something like an assignment in the upper left-hand corner, you see here, just assign an input is 1 plus some sum. It actually gets represented as a tree inside the program. So there's an assignment at the top. And then on the left-hand side is a reference to a variable in, and on the right-hand side is the addition of a variable reference and a constant. And this gets represented in a .tree file, which gets put in the output directory from Verilator. And you see this kind of same tree structure with the 1s and the 2s in front. And there's then the pointer, and it also tells you the source code. So like, for example, this assign W, the first line here says E29 in the squiggly brackets, curly braces, which means E, which is the, I guess the 5th or 4th file, line 29 is where that particular declaration is. There's a bunch of other information that is helpful for debug too. So to kind of wrap things up, the first thing I'd like to hit is Verilog-perl. So Verilog-perl shares the front end with Verilator. It's a Perl test bench, Perl toolbox, which also has some utilities associated with it. So it has the full preprocessor, and it has a preprocessor you can run standalone, which is really useful for debugging what other simulators think the preprocessor output should be. There's a tool to print the design hierarchy, which a lot of people use to then create file lists to feed into other simulators. And there's a tool called VRename, which is a quick way of renaming signals and guaranteeing consistency across a file. So a lot of people use that particular tool. I'm also happen to be the author of Verilog-mode for Emacs, which is certainly the most popular tool I have and probably one of the most used open source tools in the industry. This is used to extend the Verilog language by the presence of the autos. So down at the bottom you see I have an auto logic and auto inst. And by hitting a keystroke in Emacs or running it as a standalone tool, basically you can explode this into the signals that connect up instances and explode the equivalent of kind of a dot star using a regular expression. So on the right-hand side, you see it hook up these signals. The nice thing is that by using this tool, the output of the tool is always Verilog. So even if you don't have the tool, you can ship this autoed code to someone else, and it's still totally valid Verilog. So you'll see these autos in a lot of the IP vendor codes. The IP vendors are perfectly happy to leave these in because, again, the output is totally valid Verilog. And actually, it's kind of funny because here in Boston, CABIM, we're hiring verification engineers like mad, and I have an interview about every 2 weeks, and I kind of twice a week or so, and I ask people, what kind of tools you're using, and about once a month, someone will say, no, and I really like Verilog-mode, or I'm using emacs, and I like Verilog-mode, or I'm using Verilator, and it's kind of funny because say, how do you like it? It's like, it's pretty good. It has this little nit. It's like, okay, that's kind of interesting, and then they kind of realize who I am, and I'm like, you can put something up on the web, and we can fix that for you. Just happen to mention on the forum. So please try to tell us what you like and what you don't like about the tools, because if you don't tell us, we'll never be able to fix it. So anyhow, why might you be interested in Verilator? Well, it's supported. It's been in support for over 19 years now, so it's been enhanced for quite a while. Open source can help you. It's easy to run on laptops and developer machines. You can get bug fixes really quickly because you can go in there and edit source if you want to, and you can actually get some money off on your commercial licenses. You almost certainly want to keep your, at least if you're a large scale simulation house, you want to keep your commercial simulators. You're going to still probably want a SystemVerilog verification environment, and you need something to run all that analog stuff and do back annotation of SDFs and all kind of those full featured simulation things. And most people also want a reference for sign-off. But one of the big advantages of having open source simulator is 90% of your simulations probably don't need all that fancy stuff. You're not running analog with them, and if you can move 90% of your simulations to something open source, that's free, means you need only 10% of the license cost. So that makes a huge amount of money difference. And you can spend that money instead on, for example, simulation machines. So you get a huge amount more throughput, even more so than you would see by just performance input impact. You actually get the sort of a effective performance increase because you can spend that money on simulation machines rather than simulation licenses. So finally, again, I'd like to encourage people to contribute back. The value is sort of in the community. That's the way open source works. So please try to use it forums, even just to say, I tried it and I like it, or I use it, or I tried it, but it just doesn't do quite what I need for the following reason. But maybe I'll check back in 5 years or whatever. That's useful. Obviously, if you have to report a bug. And if you'd like to try to submit a patch, even if it's something very simple because you noticed a spelling mistake on one of the pieces of documentation, that's still very valuable to get back. So if you're interested, the source code is obviously available at Veripool.org, and that's where you'll find the forums and mailing lists and all that sort of things. And just last night or this morning for you guys, I posted this presentation at Veripool.org under papers. So if you want to get it or download slides, you can get that here. So thank you very much, and we'll open it up for questions.
Okay. So thanks, Wilson. So we're going to go to any questions now. Any questions in Bristol first? Yeah, there's one question, Wilson, from Trevor Southwell, Bob Imagination.
Hi, Wilson. I was just interested in what your timescales might be for a working VHDL implementation in Verilator. You mentioned it, but you didn't say when.
Yeah, as with a lot of things at Verilator, I'm actually not the one doing it. So there's a contributor that's working on it, and I know he was kind of gung-ho. So I don't think he's actually announced when he would be finished. So I think you'll have to post something on the forums. There's a bug on VHDL support, so you can post a question there asking when it's going to be ready. He's running a few tests, and a few very simple things now. So there's some signs of life.
Okay. Any others from Bristol?
Okay, just a follow-up on that last question from Jeremy Bennett of Embercosm. We provide Verilator support services and work closely with Wilson. One of the way you can accelerate VHDL support is actually by investing in, obviously I'd like it to us, but one of the commercial providers of Verilator support, because it's just hours it takes to get the job done.
Any other questions from Bristol? So, keep getting Anthony Wood, again of Imagination. Oh, go on.
Hi. I just wanted to know about coverage. There was some mention there was some test bench support. Just wonder what coverage support there was and perhaps assertions.
Yeah, assertions are fairly simple, I guess I would say. Basically, non-temporal assertions are supported because that was what the people that added it needed at the time. There was a little bit of code put in to support some temporality, but I don't think it's probably not really ready for prime time. So if you're doing something very simple, I think that works fine. If you want something more complicated, you want to run full complicated PSL like assertions, it probably needs a little bit of work. As far as coverage, it's sort of the same story. Support was added for dumping simple coverage statements into a tool called SystemVerilog, which is sort of a wraparound System C. So that all still works. It then feeds into a database called CovVice. You can see on the Verilog website, which actually is, I think, well, I'm obviously biased, but I think is actually pretty superior to some of the commercial tools in terms of the database that it supports. You can actually support potentially, tens of millions of runs, which a lot of the commercial coverage tools can't really handle. But the actual form of the coverage statements is not the same as full temporal-based coverage like you can do in most of SystemVerilog. So if you're willing to live with the constraints, it can do a pretty good job, but it's not exactly the same kind of thing you'd get if you just compared it with commercial tool
coverage. Thanks, Wilson. There is a question online from Gareth Edwards. Gareth says he saw a mention on the forum of using Verilator with til/truss. Are there any examples available of that, please?
Actually, one of the developers of til/truss actually works here at Cavium, and it's been. I know someone was doing it at least a couple years ago. So I remember the questions. I think there might be something on one of the forums about it. I haven't seen any questions recently, which either means it's working fine, or that person's not, or those people aren't using it anymore. It probably just works fine, because til and truss are pretty C++ based, so it's probably just working. But you'd have to try it. Because I don't personally use til or truss.
Okay, I think we're going to switch to Cambridge now and ask if there's any questions in Cambridge. Okay, Wilson.
Hi, Mike. Sprite here. No, I don't think we've got any questions in the room.
Okay, so we'll switch then to Grenoble.
Okay, yeah, one question from Joseph Boulan from Calrac. Hi, I'd like to know about the contribution. What is exactly the kind of license? Is it purely GPL or LGPL? Meaning that if you contribute, you need at once to provide your contribution. What's happening if you want to develop a tool based on that? What is it exactly? Do you have to have a commercial license?
Yeah, so, well, I'm not a lawyer, but basically the licenses that Verilator itself is under, it's actually what's called a dual license. So it's either GPL v3, lesser GPL v3, or at your selection, the Perl artistic license. So, again, not being a lawyer, what that dual licensing was intended to do, and I think does, is that you're free to, even more so than a normal GNU license product, you can take the output of Verilator, you can take the Verilator libraries, you can combine them into another tool, even a commercial tool. However, what you can't do is you can't offer for sale something that has basically the same, the internals of Verilator without contributing that source back. So, if you're going to really offer a commercial tool that does that has the internals of Verilator, you really need to ask a lawyer, and obviously we would like to have people contribute back. However, if what you're doing is using a modified version of Verilator inside your company, that's perfectly fine. If you're using the libraries of Verilator in a commercial tool, that's also fine. So, for example, if you Verilate a model and that is your IP, and you want to then sell that as a simulator for your chip IP, that's also perfectly fine.
Any more from Grenoble, Francois?
Okay. Yep. Yes. An additional question, please. Do you have an idea of the size, the maximum size of designs that are simulated using Verilator?
I know it's been used on some very large chips. The limit is actually probably less so with Verilator as it is with having to compile up all the models. So if you have a really huge chip, for example, like a 32-core chip or something like that, what tends to work better is rather than using Verilator on the entire chip, what you do is you use Verilator to compile up each of the cores. You can then instantiate the cores in a top-level model and simulate the cores. The reason you might want to do that is Verilator actually flattens the entire design. There's switches so you can not do this, but if you just use it out of the box, it's going to flatten the entire design, and you're going to get a huge number of models that you then need to compile up. There's instructions on in the man page for how to do that efficiently. So you can use something called distcc and object cache and compile in parallel. So that makes it a lot better, but it's still less efficient than it would be if you kind of apply a little bit of brain power and say, okay, I'm going to segment the design so that all the pieces that are absolutely identical you can have separate, have as a single model that's instantiated multiple times, which is not that unlike, if you try to run, some of the multi-CPU commercial tools, they're fairly similar. They like to be partitioned, and you get much better performance if you partition than if you just try to throw something huge at it.
Any more
Maybe
questions?
Another question, the last one from
Yes, Francois, any more questions from Grenoble?
Yes.
Okay.
Another question is there any plan to support UVM on top of SystemVerilog for verification?
Yeah, so if SystemVerilog could be considered, well, let's say Verilog is probably about level 1 in complexity. SystemVerilog is probably about a 7 in complexity. Getting to full UVM is probably a 9. So we're not yet at full SystemVerilog support. When we get there, UVM kind of, even though you would think that UVM is SystemVerilog, which of course it is, it requires sort of a number of things that are not really well spec'd. Even the preprocessor is an example of this. If you do what the spec says in terms of preprocessor, you get something. But if you really look at what you need to support, even the UVM, just the preprocessor constructs, which Verilator does support, by the way, the preprocessor part of it. There's all these sort of things that are unwritten in the spec you need to understand. So I think it's going to be a long wait. It's certainly possible. I hope we'll get there eventually, but looking at the amount of work to do, it's certainly not going to be the next year or two. Unless, of course, a lot of people speak up and are willing to put dollars behind it, then some of the firms can hire a lot of people to work on it.
Just following on that, I have one question, Wilson. What sort of VIP is available to go with Verilator? Is there any concept of Verilator VIP?
No, right now there is no Verilator VIP. So, I suspect that looking at the way the industry trends are working, that there probably won't ever be any. It'll probably move more towards using UVM eventually, or one of the other similar things. Whatever UVM is gets replaced by.
Okay, we're going to switch to Eindhoven now to see if there's any questions from Eindhoven. Martin?
Currently, there are no questions from Eindhoven.
Okay. So some online questions. One from Praveen. How does Verilator exploit multiprocessing?
Right now, unfortunately, Verilator itself doesn't. However, the files that it generates have all the appropriate multi-threadedness in them. So one of the other reasons that if you have a very large design, if you split it up between multiple Verilator runs, is each of those cores could then actually run on a separate processor. So as long as you write the wrapper right, you can actually get multiprocessor performance. Being able to actually take in a single design and split it between multiple cores, there's been several PhD projects that have been looking at it, although we haven't seen any patches yet. So, hopefully at some point someone will step forward and be willing to do that. As I'm sure you all appreciate, it's kind of a hard problem. It's not an easy algorithmic problem. It's very easy to make something that performs, maybe 1.5 better or 2 better, but to get anything more than that is very difficult. Actually, and one of the other common questions as well, what about running Verilator on GPUs? GPUs tend to be very good at floating point and not so good at integer math. And they're also not very good at having each thread kind of do something different, which is really what you want with Verilog. If you kind of think of your design, there tends to be very few cases where in your design you have the same thing replicated 100,000 times. It's much more, there's 100,000 different things which are maybe replicated 2 or 3 times, which doesn't really fit in with the way GPUs work well.
Okay, Wilson, we've got one last question online. Ji Zhu, could you talk a little bit more about MATLAB integration?
Yeah, there's or at least there's a pointer on the website. One of the users Verilator, basically they were running MATLAB, and what they wanted to do is they wanted to take a Verilog design of a piece of Verilog with a piece of one of their designs, and they wanted to run it sort of inside a MATLAB simulation to see if the design was working correctly from a MATLAB perspective. And one of the traditional ways of doing this is there's simulation bridges. So you run a simulator along with MATLAB, and it passes the information back and forth to MATLAB. And as with most co-simulations, this approach does work, but it's kind of a pain to cobble together, and it tends to be pretty slow because there's all this information passing in. Usually you spend more time formatting the data and crossing between these multiple processes than you do actually getting any real simulation work done. So the technique that was used was, Verilator model, generate C++ code, and then create the appropriate magic inside MATLAB to instantiate that C++ code, as you kind of would as a normal C++ plugin. Now, MATLAB doesn't need to know what's Verilog, and that works pretty good. So the thing to do is look at this tool, which is actually available on another website, but there's a point on the Veripool website towards it.
Slightly over because you had so many questions, Wilson. So I guess the last thing is just to say thank you. We'll give you a virtual round of applause in Bristol and around the world. So thank you very much, Wilson.